Okay. Thank you very much for coming. I hope this is going to be a fun talk. I do want to start with a disclaimer. So this is my first time on hardware. I'm not a hardware guy. I'm a software guy. And I look at this stuff and I go, wow. And there is a little bit of hardware in my talk that we actually built that people more talented than me built. But if I say something stupid about hardware, please interrupt me and say, no, this is wrong. Here's how it. So I don't mind. I'm not a hardware guy, so I'm a little bit nervous about that. Okay, so the title, the goal of my talk today is to present the work we've been doing at Project STEMA at Microsoft Research. Microsoft Research, for those of you who don't know, is a research lab that Microsoft has had for many years. And the number one job for us is to push the state of the art in research in computer science. So we definitely are not the hardware research lab. Now, STEMA stands for Secure, Trustworthy, and Enhanced Memory for Azure. Azure is the name of the cloud that Microsoft operates, and it's a big business for Microsoft. The company is very concerned about security and reliability issues with the cloud because they make a lot of money off of it. Now, for the past 6 years, by being in this research lab, we had front row seats at the understanding the work done on Rowhammer in both academia and industry. And this gave us a unique perspective into this problem. And I think this talk is going to actually share some of that perspective with you. And I think it's actually quite interesting. So being in this research lab, I wear two hats. I wear an academic hat and I wear an industry hat. And if I put on my academic hat, I would be really puzzled by how industry has chosen to respond to the Rowhammer problem. And I hope to shed some of the light as to why industry is behaving the way it is, or sort of how they sort of function. I hope that this will help researchers understand a little bit better what the right problems are to work on. At the same time, I spend time in the DRAM industry, and the DRAM industry is also puzzled by what motivates researchers to do this work. And again, I'm actually going to talk a little bit about that, and I'm going to explain the tremendous impact that the researchers have made into this area and how important that was. Okay. So on this slide, I like to motivate this work by talking about nation-state attacks. This is a security crowd. I don't have to spend a lot of time motivating why nation-state attacks are something very concerning. What I have on this slide is a couple of news snippets from articles about nation-state attacks that not just only occurred, but they were in fact successful, and they're all targeting Microsoft. But obviously, Microsoft is a big target, no doubt about it, but it's not the only target. Every software company is facing these things. The problem with nation-state attacks is not, yes, I work at Microsoft. We want to make sure that the cloud business continues to function properly. But in my mind, for the societal good, the problem with nation-state attacks to the cloud is that, for better or worse, our infrastructure has taken a huge dependency on the cloud. So making sure that nation-state attacks actually are not successful is very important, not just to the cloud operators, but to sort of national security. So nation-state attacks threaten not just the survival of the cloud, but national security. Now, I'm going to make even a more bolder claim. And again, for this audience, I expect you guys are not going to be surprised, but sometimes I give this talk to all sorts of other people, and there's a lot more eyebrows being raised. But here's my argument. My argument that when it comes to nation-state attacks, those headlines, they're just noise. We have not seen the worst yet. And the reason why we haven't seen the worst is because we haven't, happily so far, we haven't had to operate the cloud in times of open conflict, at least in the Western world. And the problem with open conflict is if you look at those nation-state attacks that were doing data breaches and stealing email, when it comes to open conflict, the goal is not necessarily to steal email, but the goal is to actually shut down the cloud. And by doing that, you're going to cause widespread pain for the whole society. Now, how can a nation-state cripple cloud infrastructure? So the nightmare scenario that really sort of resonates in my head and makes me paranoid is, imagine that we wake up one day and we learn that a massive number of cloud servers, whether Microsoft or other cloud operators, start actually rebooting, shutting down, or hanging in waves. making the cloud inoperable, not being able to function. This will be a pretty big problem for national security and for the industry and economy and so on and so forth. What might such an attack look like in practice? So let me give a very simple two-step recipe of how to mount such an attack. Imagine that a nation state, by the way, when I see, you guys know, but when I talk about nation state, I talk about, smart people, well-educated, well-trained with big budgets that have time to go hone their attack tools and mount this attack all at once. But imagine that a nation state acquires knowledge of a hardware vulnerability that can crash a cloud server. And we can, it creates a program, let's call it Rowhammer.shell. And step number 2, I'm gonna just buy a whole bunch of virtual machines. VMs here stand for virtual machines, so that I can scale out this attack. And all at once, I run this script, and I crash a whole bunch of servers. Rowhammer is a DRAM security vulnerability, and unfortunately, it fits this kind of. It's a prime example of such an attack vector. It really fits this problem very well. Now, what is Rowhammer and why is it dangerous? I suspect some of you know a lot about Rowhammer in this audience. So what I'm going to do is I'm going to give the world's shortest tutorial on Rowhammer that just spans 3 slides, 2 of which are pictures, super fast. This is a DIMM. Okay, a DIMM is basically a PCB that holds DRAM chips inside of it. When you open a server, and I want to say one more thing. When it comes to the cloud, nowadays people are confused, or people mix GPU servers with what is called compute servers. The GPU servers, for first approximation, are these beasts that mostly NVIDIA sells. The work I'm presenting in this talk is about more traditional compute servers. And when you open one of these compute servers, you see these DIMMs, and there is a lot of them. There's actually a whole bunch of stuff about DIMMs that people don't know. Everybody's obsessed about CPUs. The biggest cost in a cloud server is not CPUs, it's DRAM. The largest amount of silicon spent in the server is not CPUs, it's DRAM. So DRAM is sort of this thing at the bottom that people know it's dumb, we read things, we write things. It's a huge problem that has received a lot less attention than CPUs. There are DRAM chips on this PCB in this DIMM, on both sides. I'm not showing you the back side, but it looks very similar to the front side. If you look inside of this DRAM chip, you see billions of cells. Each cell stores a bit of information. Each cell has a transistor and a capacitor. And this is not a real picture. It's kind of something more that builds a mental model as to how it works. And Rowhammer, what it does, it corrupts memory. So let me explain how that is. The issue arises because when you actually access a DRAM row, so when you actually look up for data, what you do, you access a DRAM row. So DRAM is rows and columns. You access a DRAM row, and when you access a DRAM row, there is a little bit of disturbance that you actually create on nearby rows. Here, row R will disturb rows R-1 and R+1. So to mount Rowhammer, I go access row R repeatedly. And when I access this row at a high rate, I'm going to cause a bit to flip. And in my example here, I'm flipping a bit in row R-1. A little bit of terminology. The row I access repeatedly is called aggressor row. The rows where I flip bits are called victim rows. What's interesting here, and it's really important, is that the program that accesses that row R might never access row R-1. And in fact, it might not be even allowed by the OS or by the hardware to access row -1, and yet it flipped a bit there, and that's why it's dangerous. A couple of more other things. So the disturbance affects the adjacent rows, but affects all nearby rows. So here in this example, I'm showing rows R-1 and R+1, but it also affects R-2 and R+2, R-3 and R+3 to a lesser extent. So it's a physical effect. The further away you are from aggressor row, the less of a disturbance you receive from that aggressor row. So there's going to be a row very far away, which to a first approximation is really not disturbed, or the amount of disturbance it receives is negligible. Okay, so it's one of these sort of physical sort of form of attacks. So what do I do with this? I corrupt memory. And what's bad about corrupting memory? Well, there's sort of 2 side effects. One is that I can create a security vulnerability. And The security research community is in love with showing how I can use Rowhammer to break into your favorite system. And you name a system out there, and boy, there is a paper that shows how you can use Rowhammer to break into that system. It's not surprising, right? I mean, you know, if you flip bits and you flip the right bit, I can actually break into the system, into any software system. Browsers, hypervisors, HGX enclaves, you name it, they've broken it. And it makes sense intuitively because software systems work with the assumption that the DRAM is reliable. And what that means is that when I read something from DRAM, I read what I last wrote into it. I don't read something else. And Rowhammer breaks that convention and bad things happen. But the second problem is that it actually makes it really trivial to have servers reboot, shut down, and hang. And this is a problem that's a lot less intellectually stimulating for academic researchers at least, and it receives a lot less attention. But in fact, coming from industry, this is a much bigger problem for industry than the actual security vulnerabilities demonstrated. I can talk a little bit more why that industry looks at it that way. The bar for mounting Rowhammer to cause the second problem is much lower. And you can, like I said before, you can scale it out and cause this as for on a lot of servers, and that's a big problem. The one on top, it's a lot of work to mount that, and it's kind of hard to do it at a large scale. And yes, you can do these things, but if you want to mount data breaches, with all due my respect, I think there are probably easier attack vectors than Rowhammer to do that. I have a graph here that shows whether the Rowhammer problem is getting better or worse over time. And this graph has a lot of sort of Rowhammer and DRAM terminology, hammer counts and process nodes, or hammer counts on the y-axis, process nodes on the x-axis, 1x, 1y, 1z. Maybe some of you can decipher what those are, but what I'm going to do is I'm going to translate this in English. So the y-axis is just a metric that measures how resilient the DRAM is to Rowhammer. The x-axis is different process nodes, different, sort of lithography nodes, and I put dates there. And when you see 2021 H2, that's, by the way, that's a kind of like the way Microsoft uses. H2 means second half of that year, and H1 means first half of that year. So as you go to the right, there is more newer DRAM. And in each date, in each date bucket, I have 3 bars corresponding to 3 DRAM vendors. Something like 95, 96% of all DRAM in the world is made by Micron, Samsung, and Hynix. And those are the 3 DRAM vendors I'm showing here, but I'm obfuscating them. It's really not important. They're sort of all similar from this point of view. But the point is that the resiliency to Rowhammer drops over time. And this is sort of, in some sense, is a little bit counterintuitive because you expect the problem to general problems get better over time, not worse. The reason why it's getting worse is because memory, like any silicon, they like to make things denser and denser and denser and denser. And as you make things denser, these disturbance effects actually start being much more pronounced. They get worse over time, not better. And that's why. So it makes sense. One more thing I want to say about this graph is that when we measured this, we disabled in DRAM Rowhammer mitigations. I'm going to make a claim that I don't have evidence for it. It's something I believe. But what I believe is that all DRAM today comes with internal Rowhammer mitigations. Every single DRAM chip, at least the ones that we use in laptops and servers. Because the DRAM under it is so bad that in the absence of this Rowhammer mitigation that they have already, that's far from perfect, you'll flip bits left, right, and center. So in this graph, we turn that off. How do we turn this off? This is where the hardware guys that I work with, they're sort of really cool, did some magic, and I'm going to show you how they did it. So the bottom line is that DRAM is actually quite unreliable, and Rowhammer makes DRAM vulnerable. And that ends the background and the motivation of my talk, and I'm going to actually move into the results part of my talk. And I want you to leave with 3 high-level messages. If everything else is confusing, this is sort of the 3 things I want to communicate in my talk. Number 1 is that researchers have played a tremendous role in keeping industry honest. Okay, and I'm very, very grateful for that. The second part, the second message, which is a little bit, might be a little bit hard to sort of makes sense, but hopefully the talk will elucidate some of it, is that my goal is to fix this problem. And and that's what I mean by impact. And if that's your goal, the way to do that is to work with the industry and not against it. And I'm going to explain that, at least that's my experience, and I'm going to explain how I arrive at this conclusion. And the third problem is that Rowhammer is far from being a solved problem. And why is that interesting? One of the things that you're going to see in this talk is that for the first time now, DRAM is going to have protection, is going to have new mechanisms inside of it that are actually very sophisticated, much stronger than before, that if they're used correctly and configured correctly and they do the right thing, they can stop Rowhammer. This is for the first time we have this, but yet I'm going to argue that Rowhammer is far from being solved, even with these protections in place. This is, by the way, for those of you who might know, it's called PRAC. I like to call it PRAC. A lot of people, the DRAM industry is terrible at acronyms. They always like butcher things, so they call it PRAC, which is, I think, is a terrible name. But anyway, I'm going to call it PRAC or PRAC, and I'm going to switch those terms interchangeably. Okay, this is a timeline for work we've done in the past 6 years in Project STEMA. This is just a roadmap for my talk. Don't have to read this. I'm not going to present all the work we've done. I'm just going to talk about some of the highlights. So we started in 2018. At the time, I knew nothing about DRAM. I know a lot more. A lot of the people in the software in the lab who are software people, they think I know a lot. I'm the DRAM expert. And I go, oh my God, you guys have no idea how little I know about DRAM. But I knew nothing about DRAM. And I was reading these papers on Rowhammer, and I went around the company and I actually asked people in Azure, both at Microsoft, people, in some other large cloud vendors that you might guess. And the DRAM vendors, is Rowhammer a problem that is going to be concerning? So this was in about 2018, before 2020. And at the time, the academic papers were showing how they flip bits on DDR3. DDR is the type of memory used in these compute servers that I mentioned. I want to make a couple of things to make clear. DRAM is all the same. Whether it's DDR, LPDDR, HBM, it's the same DRAM, okay? DDR and all these things refer to the way in which the CPU talks to the DRAM. And for compute servers, we use DDR, and it has certain properties. For GPU servers, the GPU cores often talk to HBM memory, which is still DRAM, but they use HBM, which is a sort of a different beast than DDR. And right now, if you buy a compute server, fresh off, if you go order one, it comes with DDR5 today, 2025. In 2018, 2019, DDR4 was just coming out, and it was like the cool new thing. So I went around and asked, is Rowhammer a problem? No, it's not a problem. That's a DDR3 problem, and DDR4 is safe. And I actually took some snapshots and there were a lot more bolder claims than this. Unfortunately, I didn't save them, and since then they've erased. These companies have done a really good job of covering their tracks. But there are all these experts out there who claim that DDR4 is Rowhammer free, which is a very, very strong statement. So remember, I said that there is this new thing, PRAC, that comes that I think is way stronger than anything before. I don't think DRAM is going to be Rowhammer free anytime soon. So very strong statements. But what happened in 2022, there was a breakthrough that led to a change in this attitude. There was a paper published from ETH Zurich, and what they've actually called Trespass. And what they've actually done, they took a whole bunch of DIMMs, and they basically started flipping bits using Rowhammer. This is a snapshot from their paper. What I'm going to do is, it's a little bit hard to read, so what I'm going to do, I'm going to basically show you this table, which is just some of the numbers from the previous table, that I'm making them bigger here. And what you see here is that they were able to flip bits on modern DDR4 devices. That is a date. The first two digits represent the year. So you see 2019, 2016. 2019 was very modern DRAM at the time. And what they did was they used these sophisticated patterns, and no single pattern worked on every single DIMM. What do I mean by pattern? So DDR3 papers, they showed how to mount DRAM using single-sided attack. Single-sided is what I showed in that slide. You have one aggressor row. Double-sided means I have two aggressor rows that surround a victim row. That's on two sides of the victim. What these guys did was 9-sided, 19-sided, 14-sided, so much more sophisticated things. And at the time, it was a little puzzling why these things work, but I'm going to explain why that is. It actually makes total sense why these multi-sided attacks work. It has to do with the fact that all the DRAM industry has done for DDR4 is they've put in this anti-Rowhammer circuitry inside of it that did an amazing job of stopping one single-sided or double-sided attacks, but they were far from keeping track of multiple-sided attacks, and they succumbed to these kind of things. And there's really no good solution for them that way. Okay, so there was no single pattern. When they flip bits, they flip a lot of bits sometimes. The same group of people 2 years later published a paper called Blacksmith, where they really honed their attack tools and they show how they can flip bits on every single DR4 DIMM they tested. Okay, so if whether before 2020 we had this piece of news that DDR4 Rowhammer is free, after 2020, and at the time this was a very popular sort of phrase, it turns out that this news was fake news. Okay, at the time, now everybody talks about fake news. At the time, it was more of a newer term. So I hope I convinced you that researchers have really helped keep industry honest, and they've done a tremendous job, and they continue to do so. Now, back to Project STEMA, back at Microsoft, and I'm like, okay, guys, DRAM vendors have told us DDR4 is free, is Rowhammer free, is not Rowhammer free. And it's like, oh yeah, Stefan, don't worry about it. What these researchers have shown is they've shown they can flip bits on client-grade DIMMs. What Micron, Samsung, and Hynix sells to Microsoft is server-grade DIMMs. I have no idea what the difference is. To these days, I don't understand what is client-grade DIMM and server-grade DIMM. I can take some guesses, but I don't fully understand. But they're like, don't worry about it. Microsoft DIMMs that these companies sell to Microsoft that are safe. So what we've done was we started sort of investigating this issue, and we built what I think it's a state-of-the-art software and hardware DRAM research lab at Microsoft Research. I have some pictures here. On the bottom, you see Azure Blades, 3 generations of Azure Blades. About every 2 years, Azure specs a new blade, and they put these new blades in the data center. These blades are really not meant to run on benches. They're meant to run in racks in cooled data centers. So you have to kind of build all sorts of concoctions to put them up and be able to have them function. On the right-hand side at the top, we have a bus analyzer, which we're able to actually understand all the DRAM commands that the CPU sends to a DIMM. And that's a tremendously useful tool. And on the left-hand side at the top, we have a fault injector, and I'm going to talk a little bit about that. And with this sort of tooling, and I'm skipping over a lot of details, we took the famous server-grade DIMMs, and these are DIMMs that Azure bought. These are real Azure DIMMs, and we started mounting the same sort of attacks, and voila, you can flip bits. And we didn't flip a lot of bits. The reason why we didn't flip a lot of these bits is because we didn't try too hard. We kind of said, wait a second, you just told us that server-grade DIMMs are safe. No, they're not safe. What are you guys talking about? This was 2019, 2020. Server-grade DIMMs are susceptible. We went back. So the high-quality server-grade DIMMs are susceptible. And the next thing we heard was, yeah, they are, but if you want to mount an attack, you have to mount it from a virtual machine in Azure, because Azure everything is virtualized. And it's really important when you mount these attacks to be precise on how you lay out your aggressor rows. You have to know adjacency inside of the DRAM chip. And it's very hard from a virtual machine to really reverse engineer the so many address mapping layers going all the way to the DIMM. An attacker will never do that. So we said, okay, it's pretty hard, and we started looking at it, and there are many layers, address maps layers. On the left-hand side, I have a program that you run to mount Rowhammer, and it uses virtual addresses, and they get translated to physical addresses, and you have virtualization layers. In general, these kind of maps, I'm not going to talk about. They're not trivial to reverse engineer, but they're pretty easy. A lot of you guys probably know how to do this. It's not. We never think physical address like those address maps are actually secret or anything like that. And I mentioned a whole bunch of papers then. But then from the actual system physical addresses to reverse engineer what is called bus addresses or media addresses. Those are actually underspecified. There is really not good documentation for them. So it's hard to actually reverse engineer apparently. So I have a little diagram here to explain what that means by this map. So I show a CPU. MC there stands for a memory controller, a DRAM controller that talks to a DIMM. And the memory controller receives an instruction saying load this physical address, 0x1234, meaning go do a read at for this particular physical address. And the memory controller maps that into something that to the DRAM. It says, oh, I want to read rank 0, bank group 1, bank 0, row 74. Don't worry what these things are. There's just ways to address DRAM. So I'm going to read row 74 in this DIMM, this particular DIMM or set of DIMMs. And that's a map. So how do you actually reverse engineer these maps? There are actually researchers who have used side channel attacks to reverse engineer these maps. And I mean, it's great to do that. That's a lot of work. We've done something a lot simpler, which is we bought a bus analyzer. So we actually can interpose on that bus and see everything that's going on. And it becomes pretty straightforward to reverse engineer these maps. This is the bus analyzer we purchased. There is a company in New Hampshire that makes these bus analyzers. They're pretty good guys. I like them a lot. It's not cheap, but it's not that expensive. It's a research group at any average university. Well, now the funding is pretty bad given the current situation. But a couple of years ago, it's definitely within the budget of that. This is as expensive of how much a professor pays for funding a graduate student for a year. It's not a lot of money, relatively speaking. And all those maps that were hard to reverse engineer and proprietary and so on, this is the map that Intel uses on Skylake server class CPUs. So it's trivial to reverse engineer. We reverse engineer all of them. So that's this DRAM controller map in the middle, but there is also a map inside of the chip that might have to do with the way the motherboard routes the signals, or maybe the chips actually does some scrambling inside of it. And how the hell do you reverse engineer inside of the chip what's going on? So let me give you an example. The memory controller might say, I want to read the row 0 or row 1. The chip doesn't have to make row 0 or row 1, doesn't have to have them adjacent. I mean, the DRAM can scramble that. The DRAM will still function. Everything will work. They don't have to do that. So, what we did was we got inspired from some methodology from previous work. And it's sort of interesting that if you are able to mount Rowhammer and flip a lot of bits, the pattern in which those bits flip tell you about adjacency. That's a really nice way to reverse engineer these maps, not the only way. So let me kind of build a little bit of intuition. So let's say I hammer row K. Yes, row K here. What's going to happen if I can flip a lot of bits? I'm going to flip a lot of bits on rows K minus 1 and K plus 1. But then I'm going to flip some bits on K minus 2 and K plus 2, not as many. As I go further and further away, I flip fewer and fewer bits. And if I can look at which bits I flip, now I know adjacency. Okay, I hope that kind of makes sense. And we've done exactly, for this to work, by the way, you want the DRAM to really succumb to Rowhammer. So what we need to do is we need to turn off those DRAM mitigations to really hammer the heck out of this DRAM. So how did we do that? We built a fault injector. And this is, by the way, when I say we, I had very little to do with this. I was like just in awe and cheering on the sides. This is the first version of the fault injector. And what this fault injector does, it suppresses DRAM refreshes. This is a type of command that the CPU sends to DRAM. And what I said, I want to turn off the internal DRAM mitigations in the chip. And what this does, it just suppresses DRAM refreshes. It turns out that by doing this, you effectively turn off in DRAM mitigations. I don't have time to explain why that is. You have to trust me here on this thing. And the way this worked is you had a button there, and if you press the button with your thumb, you would basically suppress refreshes. And if you release the button, you re-enable them. That was version 1.0. In version 2.0, these guys added 3 more switches to it. It was more reliable that way. I'm not going to go into the details of what's going on here. And this is the sort of thing that we work with for a while. This is the sort of the layout. At the bottom, we had the fault injector with this big button that you have to press. In the middle, we had the bus analyzer, so we can actually see what the commands that are received by the DIMM that sits on top. So we know that if we don't touch the button, we see the DRAM refreshes, but if we actually press the button, the DRAM refreshes get suppressed. And yeah, Thank you. And yeah, what we are able to do is to reverse engineer row adjacency. So for this particular DIM, if you look at that row, it has 2 full adjacent rows, but this other row has 1 full adjacent row and the other row is half adjacent. So there is some sort of scrambling happening inside of it. I can explain more about what that is. It turns out that we learned about what's going on. Anyway, so we published a paper that we basically said, look, we have a way to test DIMMs for Rowhammer very easily with lower budgets and so on and so forth. And we went back and we said, well, you know, crafting an attack, yeah, it's not trivial for sure, but a nation state is not that hard to reverse engineer all these maps and go do it. And then the next thing was like, yeah, but even if you flip bits, all DRAM inside these servers has ECC, error correction codes. They will actually correct these bits you flip, and it's going to be very hard. And again, the industry really likes to work terms like impossible to bypass ECC. So the next thing for us was to see how we bypass ECC. There is actually work from academia on showing how to bypass certain types of ECC inside of the server with Rowhammer and still flip bits. But at that point, I kind of had an epiphany. And the epiphany was that, well, if you take a step back, there's a common theme all along, which is that the DRAM industry, whenever they lose an argument, suddenly the goalposts have shifted now. Oh, it's not client-grade DIMMs, it's server-grade. Oh, it's not, sorry, it's the maps. It's like, okay, we're done. So I felt like I'm kind of like a hamster in a mouse wheel here running. So I just said, no more of this. This is not viable for us. So then when we actually started thinking and asking the following question, why is it so hard for them to fix this problem? So I sort of had a mindset shift in that head, which is I want to now work with industry and understand why can they fix this problem. And I'm going to talk about that. So I was saying that all DRAM has anti-Rowhammer circuitry, but the circuitry actually has 2 significant limitations. One is that it's very limited. There is a lot of rows. There are millions of rows in these DRAM chips. By the way, I said billions of there. Those are billions of cells, and there are millions of rows. And the chips, there is just not enough real estate, and it's expensive for them to actually track every single row. You may track dozens of rows, and you might be clever and intelligent, super duper, but you cannot do a perfect job just because there are just way too many rows. That's problem number 1. Problem number 2 is that the way DRAM works is that even if you detect, even if you detect there is a Rowhammer attack happening, there is a hot row. This row is being accessed a lot. The DRAM needs to find time to go do some work to mitigate that problem. And the DRAM is kind of silent. It's basically just receiving commands from the host, and it basically tries to scavenge time for those commands to go actually do some work to go fix this problem. And that's another limitation. And yeah, those are big problems. So these 2 limitations make anti-Rowhammer circuitry inside of DRAM quite ineffective. So what we did was we basically came up with this scheme called Panopticon. And there are 2 main ideas. There's a lot of detail. I'm going to skip over it. Basically, we said, well, hold on a second, guys. There are DRAM cells inside of these chips, right? And there's lots of them. Can we just add some DRAM cells and add a little bit of circuitry to just implement a counter for every single row? Why? In that way, we have now a per row counter. So every row is tracked by a counter. Very straightforward idea. The second thing is to basically, there is a signal by which the DRAM can put the host on pause when it receives a command it cannot decode. So the host sends or the CPU sends a command, the DRAM receives it and tries to decode it and it says, there is an error in this. So what it tells, it says, stop, there is an error, please resend what you last sent me because I can't understand what you're telling me. So we said, guys, let's use that alert signal to actually, if you need time to go perform Rowhammer mitigations, rather than having bit flips, raise alert. And there's a lot of, to this day, there's a lot of pushback. Alert is very expensive. You have problems. Please, thank you. Please use alert. I don't want to see bit flips. The other problem with alert is that a lot of people and security people really like, oh, it's now a denial of service attack. I'm going to create attacks that raise alert a lot. And to me, I'm like, thank God we don't flip bits. Denial of service attack, they're not good, but they're a lot better than flipping bits. And I can talk a little bit about that. Anyway, these are some pictures put together by the hardware engineer who actually really had the panopticon idea. Again, I was sort of cheering on the sides. We published a paper. We wrote a reference implementation for people to actually play it. So what we've done from 2021 was, showing up at JDEC, which is the DRAM consortium, and just banging our fist on the table. We need these two things to actually have a prey at solving Rowhammer. We work with the DRAM industry, and that took a while. The other thing I want to mention quickly was we actually made our fault injector a lot more sophisticated. We are able to basically, inside of a piece of code, you can run portions of piece of code with DRAM refresh being disabled. This is how our fault injector look like. It's programmatical. We got rid of the stupid thumb button press thingy. Now you can actually use a laptop to just do very fine-grained things, very fine-grained control, enable, disable, and that's how it looks like. And while we're sort of working in industry, we actually went and published a whole bunch of papers. And I don't have time to talk about it, but I want to mention just one sentence about the first paper appeared at a conference called ISCA. And that paper, we discovered that Intel actually, and I'm going to say a lot of things, but maybe some of you will actually, on multi-socket machines, so machines that have more than one CPU, so 2, 4, or 8 CPUs, you need to build a cache coherence protocol for every cache line across all the CPUs. And their cache coherence protocol actually hammers memory. So if you have a program that actually shares state between, uses both sockets, so maybe you have 2 threads, one on each socket that share a lock, beautiful way to hammer memory. So the observation here is that you don't have to be malicious to hammer memory. You just have to actually have inefficient programs by scheduling threads on different sockets. So this basically, again, led me to this epiphany is like, if we didn't have the simpler anti-Rowhammer circuitry, we would see a lot of bit flips due to normal workloads, not malicious workloads. Commodity workloads can flip bits. We also worked on building support for host-side mitigations, which are not great, but at least until we have this panopticon adopted, maybe we can use those. And actually, Microsoft Silicon is using these in-host mitigations until panopticon got adopted. We also built a way to actually have strong partitioning inside of DRAM. I'm going to skip over that. But in 2024, DDR5 actually came up with a specification called PRAC. And that's the snippet from JDEC side. JDEC does a great job of not knowing how to communicate properly. If you read that, you have no idea what's going on. But basically, if you translate, there are 2 techniques in PRAC. One, we have a per row activation counters. I'm going to count how many times that row gets activated in DRAM. And 2, the DRAM will raise alerts rather than it's going to let bits to be flipped. So for the first time, and that's what I'm actually sort of proud of, for the first time now, we have the mechanism to stop Rowhammer once and for all. And if you want to read about PRAC, DDR5 specification has PRAC description. Unfortunately, JDEC charges money for downloading specification. This is a battle I have not won yet. I don't know if I'm going to be successful, but if you want to read a little bit about PRAC, you can go to my website where I have an article, and it's for free. You can download it. It's stefan.take2.com, TAK2.com. Okay. And even with that, Rowhammer is far from being solved, I would argue. And the reason why that is because there are many, many, many things that need to get right for PRAC to actually work. One of it that I'm actually very concerned about is to configure it correctly. The problem with configuring it correctly is that you have to sacrifice performance to configure PRAC correctly. And the DRAM vendors have an amazing track record of never sacrificing, they're always sacrificing security in exchange for performance. So we'll see how that's going to play out. I want to mention one more interesting sort of thing about PRAC. A row in DRAM when you access spans multiple chips. And I have this silly cartoonish-like idea just to build a sense of what's going on. But that's a single DRAM row in some sense from the host perspective, from the CPU perspective. Each chip has its own set of counters. And you think that every time you access a row, because you access everything in every chip, you'll think that these counters are in sync. No, they're not. Okay, and that's actually a problem. You have these multiple counters that are not in sync. Anyway, so there's a lot of work that actually remains to be done on PRAC, on Rowhammer. So it's far from being a solved problem. So to recap, 3 messages to take away. Researchers have helped keep industry honest. Impact comes from working with industry rather than against it. And Rowhammer, we are much better than we've been before, but we're far from being solved. I want to acknowledge there are many people in Microsoft, outside Microsoft, in academia, in industry that worked on Project STEMA over the past 6 years. And I'm super grateful for all of them. This is the timeline I showed before. And I have one more slide, which is I want to ask your help. So if you're interested in actually helping us build an HBM bus analyzer, HBM is the GPU type of memory, come talk to me. I would like to work with you. It's a much harder problem than for DDR. The interfaces are not exposed. They're stacked dies. It probably requires developing custom hardware, but I'm very excited about doing these things because I think one thing I learned is that the moment you build these tools, you think you know how these things work, and when we actually build these tools and look at them, as you guys know, they work completely different. And I'm done. Thank you very much for your time, and thank you for listening.
Thank you for your talk. Do you have any questions?
You started the talk with the premise of you're deeply concerned about the cloud infrastructure going down in the event of nation-state attacks. And then once you talked about PRAC, you said that there was pushback against it from the hardware makers by saying the alerts turn into a DOS mechanism on themselves. So how do you rectify those two? Because you're like, no, bit flip's good, but DOS, oh, who cares?
No, thank you. Yeah, I said that. You're absolutely right. Thank you for asking that question and giving me the opportunity to rectify that. So just to recap, PRAC can be turned into a denial of service attack vector, and that's a problem for the cloud. That's a problem for national security and so on and so forth. You just told me that's a problem. Why are you okay with that? There are 2 reasons, and every time I say this, I say it a little bit definitively, and I'm probably say it a little too strongly, so I'm probably wrong. I spend so much time fighting Rowhammer that I'm kind of a little bit biased that way. But at least here's my opinion. So yes, you're right. But I would rather take denial of service over bit flips any times because bit flips are particularly nasty. Like if there is a way to actually do bit flips, there's no software patch, there's nothing I can do about that. Now, we denial of service attacks by actually shutting down DRAM and making the server basically slow down. What I like about that is that it's very easy to detect that. And it's very easy to pinpoint as to where that's happening, and I can actually go after that and shut them off. It's not ideal, and I would love to actually see a PRAC++ implementation that doesn't have a denial of service attack. So yes, it's a problem. And it needs to be addressed. And perhaps I said a little bit too strongly by saying it's not as important, but it's an important. The problem is when I think about the servers, there's so many denial of service attacks you can do on the server that this is yet another one. So whereas with Rowhammer, it's particularly nasty. But yeah, I hope I communicated where I stand there.
I guess when he asked the question, going back to the very first scenario of the catastrophe with the everybody booting up. So DRAM is, if I'm not mistaken, DRAM is transient memory. So let the PC boot up, fine, the bit flips will go away.
And sorry.
So the bit flips will go away. So you are okay. You are not going to keep rebooting, right? So you didn't change the boot process. You you run your script once, and I'm not sure if that as a first scenario is as easy as you pictured us.
So just to be clear, so yes, rebooting the system actually clear up the bit flip and you can start again. I have a question actually for you. So this is probably some of you know. How many times do you think a server reboots in the cloud? Come on, I don't know. 5 times a year, 5 times a month, 5 times a week?
0.
0 is the number. Obviously, the number is not 0, but it's epsilon. So no. And the reason for that is that, unfortunately, the way software gets built today, it's really not really meant for your underlying infrastructure to suddenly disappear from under you. And cloud providers actually get yelled at by their customers that they reboot machines. And the whole mentality, and I hate this mentality, but this is the reality, is that, oh, no, we can never reboot a server. This is actually a problem because doing firmware patches, you have to reboot the servers. And there is a lot of dancing happening with patching the fleet because, oh my God, we're rebooting the servers. So I don't know if that addresses your question, but I thought that's sort of interesting.
Right, we can do one more question. No more. Yeah. Maybe follow-ups. You can probably talk up the discussion to not stall the next talk. Sorry. All right, let's thank the speaker again.